Alright, hello everyone. We're going to talk about 2.1 today. And 2.1 is one of the most important sections of this chapter. We introduce the derivative and the tangent line and this is going to be the first rock that's going to build up the most important tool that we have in our class, which is derivatives. So the objectives are to find the slope of the tangent line to a curve at a point, and then use the limit definition to find the derivative of a function, and then understand the relation between differentiability and continuity. Alright, so first let's begin by defining the tangent line problem. So tangent in calculus, calculus grew out of 4 major problems in the European mathematicians were working on during the 7th century. One was the tangent line problem, the second was velocity and acceleration problem, and number 3 the minimum and maximum problem, and the fourth one the area problem. Alright, so in each problem it involves the limit, and we get to talk about the tangent line problem, and then it builds up to the velocity and acceleration, minimum and maximum, and the area problem in the further chapters. So let's begin first by let's try to define the tangent of a line. So we know how to find the slope of a curve. Now so far in the previous chapters we were only able to talk about the slope of a straight line because we only knew how to find the slope of a linear equation. But today we're able to extend that and be able to find the slope of a curve. Now the way we're going to do this is kind of interesting and very creative. So let's begin by that. First, let's think about the slope of a secant line. So the secant line happens to be a straight line, and it's here in blue. Let's see. There you go. So this blue line is the secant line. A secant line is a straight line that crosses the graph at 2 points. So now this straight line, we know how to find the slope because we did that in pre-algebra. We knew how to find the slope of a straight line by doing how much it was rising and how much it was running. Now if you guys think about it, how much is rising happens to be the difference between the two y components, right? How much is rising, so the difference between this and this. So you guys can see that's sort of described with the difference of y. How much we're running can be found by defining how much the difference between this direction, right, in between the axis. So it's going to be this minus this. So it happens to be that difference of that. Now we can find the slope of a secant line for any 2 points, right? So that's kind of sort of what we knew from the beginning. So in fact, when we defined the slope over here in pre-algebra, we said the slope happened to be the y2, the y component of the second point minus the y component of the first point, all over the second component. Now the first component of the second point minus the first component of the first point. So basically this was the slope, right? Well, now we can extend it and say, well, we can find that the slope of the secant line by doing the second component of the second point minus the second component of the first point, all over the first component of the second point minus the first component of the first point, right? Assuming that these two are the points. And if you notice, we cannot simplify the top, but we could simplify the bottom because these two c's will cancel each other out. So basically what we're saying is that every secant line can be described as this. In fact, you guys knew this formula before, known as the difference of quotient. the difference of quotient. Now delta x is often referred to the change of in x. So the triangle it comes from the Greek letter d, which is delta. So this is delta x, so it's a change of x. Same thing here, this is a change of y, so which is the difference between the y values. So now let me ask you this question. What happens if we start with this secant line? If we start with this secant line, right, and we start putting these 2 points closer and closer to each other. So what happens is that if we make these 2 points closer and closer to each other, as you guys will see here, if you notice what happens here, the 2 points are getting closer to the point that they're closer, but if you notice there's almost no distance. Well, as long as we had 2 points, we knew how to find the slope, right? Because we already knew how to find that. So what I'm trying to say here is that think about this as you having 2 points, but they're very, very close to each other. So we can use this formula to actually find the slope at that point. Well, this line is a secant, this is a secant, this is a secant. This is known as the tangent line. So the tangent line is the straight line that is kissing a specific point, right? It's just barely touching the graph at that point. It doesn't cross 2 points. It only touches the graph at one single point. That's how we distinguish between secant and tangent. Our goal is to be able to find the slope of this tangent line. Now, you knew how to find the slope of the secant line. All you have to do is rise over run, rise over run, rise over run. But now this one, we can use the same thing as rise over run, but we have to be a little more clever. Because what we're saying here, if you guys think about it, what happens to the distance between those 2 points? Delta x will keep getting smaller, So here, delta x getting so small that it's approaching 0. So that's how we were to do it. The slope, the change of y over the change of x, as the delta x went to 0, will give us the specific slope of the tangent line. And that's the main thing that we want to get from here. This right here. So we're going to call this special formula the slope of the tangent line. The slope of the tangent line. So you have your y component minus the first y component all over delta x as delta x goes to 0, right? So it's a limit definition. Now, if the limit exists, then we're saying that the line passing through that specific point, CFC, with the slope m, is the tangent line to the graph of f at that particular point. So this is actually mind-blowing, because what we're saying here is that this line has a slope, right? Because it's a straight line, we can find it using this formula. But what we also know is that this line has the same slope of this graph at that point. We're going to talk about that more in particular. And in fact, they're saying here the slope of the tangent line to the graph of f at that single point, is also called the slope of the graph of c at that same point. So what we're saying here is this is very important. So let me sum it here. This straight line, let me use a different color. This straight line slope, let me call it m, has the same slope of this point on this graph, right? At that instant, those two have the same slope, and that's amazing. That's the main thing. That's the main thing about calculus, and we're gonna define that more formally later on. But as right now, let's think about how can we use this. All right. So in example 1, we're asked to find the slope of the graph of f when c equals 2. You can apply the definition of the slope of a tangent line as shown before. So they're asking us, the question that they gave us was this: can you find the slope of the graph here? Well, what we know what to do here is we know how to find the slope of the tangent line by using this famous formula. So we're going to use this formula to be able to answer that question. So you can use the tangent line, the slope of the tangent line, to find the slope of the graph at that moment. That's the amazing thing, right? They're both the same value. So here we go. So let's apply the definition. So we have that definition here. In this case, c is equal to 2, so that's going to go here and there, right? So let's apply that. So we have m equals the limit as delta x goes to 0 of f of 2 plus delta x minus f of 2 all over delta x. So it's the same formula that you have here, same formula, except that I replace c with 2. Now, you guys remember that we talked about this problem in class. One of your classmates asked me about one similar question like this, and I said this was a very important part. That's this section. So what we're going to do is we're going to carry that limit, and we're going to sort of simplify this. Now, students sort of get lost a little bit here. So what you need to do is to translate the function in terms of its expression. So you know what's f of 2. All you have to do is replace 2 for every x you see, right? So replace a 2 there, and that's where you get your f of 2. So this right here is f of 2, followed by the minus, right? What about this one? Well, in this case, you have f of 2 plus delta x. So you're going to replace x with 2 plus delta x. So we have 2 times 2 plus delta x, followed by minus 3. Do you see how I did that there? I replace x with this quantity. And that's it. That's where students get lost most of the time. And don't forget your parentheses, you forget your brackets. And then all over delta x. Don't forget delta x. Do not forget to write the limit. It's very important. A lot of times students will just ignore it because they don't want to write it, but they will forget it at the end. So do not forget that part. So carry the limit. Continue simplifying here by using distribution. 2 times 2 is 4. 2 times delta x is 2 delta x. Minus 3. 4 minus 3 is 1, and carry the minus all over delta x. Notice what's going to happen here. 4 minus 3 minus 1 will cancel each other out. Now you have 2 delta x over delta x equals to the limit of delta x goes to 0 of 2 times delta x over delta x. Cancel those 2 delta x. And then so you end up having just the limit of 2 as delta x goes to 0. So what's the limit of a constant? The constant itself, right? There's no change there. So what we have here is that the slope of that the slope of the graph at c equals 2 happens to be 2. Now, do we knew that? Can we guess that from here? Yes, we could have guessed that by using some of the algebra that we learned in pre-algebra. Remember that this line, we can figure out the slope of this line. The slope of that line you can figure out by saying, oh, rise over run, so 2 over 1. Now, you can do this only here because that was a straight line, and the straight line has the same slope at every single point. Every single point has the same slope. But what we're saying here is, in particular, we already know that this has a slope of 2 by using this approach. Now, you're going to say, well, why do we use this approach when we knew that we could have used algebra? Well, because I want to start with an easy problem, right? Usually the problems that we're going to be working on will be more like example 2. Right, so notice in example 2, you have this curve. Now this curve, every point has a different slope. So we're going to find, in this example, we're going to find the slopes of the tangent lines to the graph at 2 different points. So we're going to find the slope at that point and the slope at that point. So now we can kind of picture this tangent line passing through that point, and we can kind of see, oh, if we can find the slope of this tangent line, then we can find the slope of the curve at that point. Similar over here, if we can find the slope of this tangent line, then we can find this, then it will be the same thing as finding the slope of the curve at that point. So I hope by me repeating this, it kind of makes sense. If you need to rewind this to hear it again, try to do that. Now, so what we're gonna do here is we're gonna do something very clever. We're gonna apply the definition of the slope, but we're gonna leave the entire thing in terms of c, because you guys will see how we're gonna be a benefit from by keeping it arbitrary. What does it mean to be arbitrary? It means in a general way where it's not specific. So what we're gonna do is we're gonna copy and paste the formula above. So we have m equals the limit of delta x goes to 0 of f of c plus delta x minus f of c over delta x. So what we're gonna do is we're gonna rewrite every function in the algebraic form. So we're gonna replace f of x, f of c. How do we find f of c? Well, you replace x with c. So for the first part, for this part, I'm just replacing x with c. So there you go. It's very simple, right? Very straightforward. The next one, we're gonna do f of c plus delta x. So we're gonna replace every x with c plus delta x. So wherever I see an x, I have to replace it with c plus delta x, followed by the square, followed by the plus 1. So there you go. That was probably the hardest part for the students, right? I keep saying that. Don't forget about the limit. So now let's go ahead and simplify this. So I'm going to go ahead and expand this. I'm going to expand this by using our basic algebra distribution process, which is going to be c squared plus 2c times delta x plus delta x squared, followed by the plus 1, followed by the minus, followed by the c squared plus 1, and there you go. Now what we're going to do here is we're going to distribute the negative, right? Don't forget about the parentheses. Students will keep forgetting the parentheses. That's one of the things the students will forget. Distribute the negative, so we're going to have the same thing here, and then distribute the negative, so it'll be negative c squared minus 1. Now notice here that, notice the things that they got canceled, the c squared and the c squared, the plus 1, the minus 1. In fact, that's a good way for you to check that you're doing this correctly. When you start canceling, and at the end, the only terms left behind will always have a delta x, because the next step, it sort of gives you a confirmation. Because the next step, you should be factoring the delta x from every single one. So that's what I'm doing. I'm factoring a delta x from here and factoring a delta x from there. So if you factor a delta x, then you're left with 2c. If you factor a delta x from here, you're left with 1 delta x. So the factored delta x is outside the parentheses, and if you notice what happens with those two, they cancel each other out, right? So what's left behind is the limit as delta x goes to 0 of 2c plus delta x. So now that we already removed this right here, now that we have removed, now you can apply the limit. So replace the delta x with 0, and then now you have 2c plus 0, which is 2c. That's so that the slope, and that means that what we just found is sort of like a formula. You can find the slope at any point on the graph by replacing the x value with c, or replacing c with the x value. So what I'm saying here is, if you want to find the slope at the point 0, 1, I'll take the x value, and replace it in the c for c. So wherever I see a c in my slope formula, I'll replace it with my x value, so 2 times 0. So that gives me a slope of 0. In fact, that's the point right there. You guys notice that the slope of this tangent line is 0, and it kind of makes sense, right? Because isn't it like when you have a horizontal line, the slope is 0? So that's a checkpoint, right? That's like something we can verify by using our algebra skills. What about that point? Well, at that point, the x value is -1, so we're going to replace c with -1, and that gives us -2. And it kind of makes sense if you guys think about it. This tangent line has a slope of -2. We can see how we can go from rise -2, round 1, right? So that's negative slope. All right, so I hope that kind of makes sense. Now, we could also have other different types of results, because remember that what we're actually finding is the slope. Remember that in some cases, some graphs, when at this point, at that point, the slope, the tangent line for that point happens to be vertical. So this point has a vertical tangent line, and what we said, that the tangent line has the same slope as the curve at that point. So if this tangent line has a slope undefined, that means that this curve at that point has a slope that is also undefined. And that's all we want to say from that. All right, so we talked about tangent lines, right? Now we're gonna connect this to our class, and we're gonna sort of give a different name. We're gonna define the derivative function. If we apply the same rule that we did above, right, this limit function, but instead of plugging in a c there, right, like we did before, instead of plugging in an actual number, we leave it in a variable form, then what we are creating here is not, we're not just finding the slope at that single point, but we're actually finding like a formula, right? You're looking for, what you're creating is a formula, a function, and you think about that function as being like a formula that will give you the slope of the function at any value of x. So this will be very, very powerful. So the derivative, we can think about the derivative as being the formula of the function to be able to find the derivative of the function at that point. Now we have, so we call this, we use this formula in different ways, right? In different ways we can use it to find the slope of the tangent line. We can call it the derivative. We can also call it the instantaneous rate of change, or sometimes also referred as rate of change. So this is called instantaneous rate of change because if we think about it, it's finding the rate of change. Rate of change is the slope, but instantaneous means that it's in that instant, meaning that you don't have to wait for 2 points to happen to be able to find the derivative. You can find this, the rate of change at that moment, and that's powerful. That was the breaking point of calculus, because you can now predict the behavior of a function by looking at that instant point. Now we call it instantaneous rate of change, or sometimes referred as rate of change, and we call this a derivative as well. And we also have a few more notations that or terms that we want to incorporate. The process of finding the derivative of a function is called differentiation. A function is differentiable, meaning that you can take the derivative of it at that particular x if its derivative exists. Now the derivative will exist if the limit exists for this, and is differentiable on an open interval from a to b if it is differentiable at every point in the interval. And we have different notations for that. We have, as you guys notice over here, I haven't talked about this, but this is known as this is read as f prime of x. So this notation is pretty nice because it distinguishes this function from this function. This is the original function over here on the right, but this right here is the derivative of the function, and the derivative will give you the slope at every single value of x. So we read that f prime of x. Now we have different ways to describe this derivative. We say f prime of x, or we have dy over dx, meaning the derivative of y in respect to x. We also refer this as y prime. We also have as d over dx of f of x. We also have dx of y. Now this one is not as common, but we'll see that later on in the semester. And so let me go back up here because I wrote another formula. This formula, it's a little bit more preferred, at least for me. It's the same formula. In this formula, instead of writing delta x, sometimes I get too tired of writing delta x all the time, so I just write h. Actually, a lot of books will do that. So this is your delta x, this is your delta x, that's your delta x. So it's the same thing, same steps as you've done before, right? It's the same step, same strategy as you've done before. The formula will follow. Doesn't matter if you have dy over dx, it's still the same thing. So they're the same thing, they read the same thing. And again, dy dx is read as the derivative of y with respect to x, or simply dy dx. So we're a little bit lazy on that way, but I hope that that's kind of helpful. All right, so it's so let's find the derivative by using the limit process. Now let me say this, that this will be required. I will have, I promise I will have a question like this in the exam. You must be able to show me that you know how to apply this derivative definition, and I will refer to it as derivative definition right here. This is the derivative definition right here, this formula, and you can use it this way or you can use it that way. I really don't matter which one you use. I will tend to use a lot of the h though. All right, so let's find the derivative of f of x equals x cubed plus 2x using the definition. So first begin by writing the definition. F prime of x equals limit of the quotient, the difference of quotients as h equals to 0. So I'll begin by setting up the equation. Remember, you have to carry the limit until the end. So come here, right, and replace for this one. This is f of x. F of x is just the same thing, right? So you're just gonna copy and paste it there. Don't forget the parentheses, right? Followed by the minus there. And then for this part, this is where usually students have trouble. Remember, you're replacing x with x plus h. Every time you see an x, replace it with x plus h, right? So because that's what they're asking us to do. So x plus h cubed plus 2, replace x with x plus h, right? And then now go ahead and simplify the algebra, right? We want to simplify this whole thing. So distribute this x plus h cubed, and remember that this is the same thing as x plus h times x plus h times x plus h. Maybe I'll write it over here. X plus h cubed is x plus h times x plus h times x plus h, right? So you have to distribute that whole thing, and I did, and I have my result is x cubed plus 3x squared times h plus 3x h squared plus h cubed plus 2x plus 2h, followed by distribute the negative here, negative x cubed minus 2x. There you go. And then, like I said before, you should be able to cancel everything that does not have an h, right? So x cubed minus x cubed cancel each other out, 2x and minus 2x cancel each other out, and then notice that every term has an h, because the next line I'm gonna factor that h, right? That's the checking point. You should be able to factor that h because every term had it. And then once you factor it out, then you can cancel. Again, don't forget the limit that's still carried, and so the result is 3x squared plus 3x h plus h squared plus 2. And now you can apply the limit, right? So replace h, every time you see an h, replace it with 0. And I did that, and those will cancel each other out. I mean, that's just multiplied by 0, multiplied by 0, so those cancel each other out. So then the derivative is 3x squared plus 2. All right. And then here we have, all right, so if you guys hear something, that's my baby girl just waking up a little bit, but All right, let's move on to the next example. We have using the derivative to find the slope of a point. We're gonna find the derivative of the function, and then we're gonna use that to find the slope of the graph at those particular points, and then we're gonna discuss the behavior of the function at 0, 0. So what I'm gonna do is first find the derivative, right? I'm gonna use the definition. Here's the definition. Here's my function. Here's the definition. Limit of the difference of quotient as h goes to 0. And then what I'm going to do is I'm going to replace this with the function. That's your function right there, minus. And then replace x plus h for x, right? So replace x with x plus h. So I replace that all over h. Now the technique when you're dealing with radicals is similar to what you did in college algebra when you're trying to rationalize the denominator or the numerator. So I'm going to go ahead and rationalize the numerator. So I'm going to rationalize the numerator by multiplying the numerator by its conjugate. So it'll be the square root of x plus h plus the square root of x all over the square root of the sum of x plus h plus the square root of x. When you multiply those two together, think about them as having parentheses around it because the fraction bar is a form of grouping. So when you multiply those together, that will by using the difference of squares, that will give you the square of this minus the square of that all over h times this quantity. So you have it down here as h goes to 0. Then we can move up here, and these will cancel each other out because the square root and the square will cancel. The square root and the square will cancel, so you're left with x plus h minus x. Don't forget the parentheses. Do not touch the bottom, just leave it as it is. You guys will see that in a second what happens. So the x's cancel each other out, right? X minus x cancel each other out, so you're left with an h times 1. I just put the 1 there just for you guys to see that there's always a 1 in as a factor, because the next line, you guys notice that the h's will cancel each other out. That's why I left the h there. So the next line, you have the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. And then now that you have removed that h, now you can apply the limit. Do you see how there's not going to be no problem anymore when you apply the limit? So replace that with 0. So now you have 1 over the square root of the sum of x plus 0 plus the square root of x. That goes away, so now you're left with adding those two square roots, which is 2 times square root of x. This is all over 1. The 1 is all over the 2 times the square root of x. And that's your derivative. We found it. But the technique here that we used was rationalizing numerator. So remember that technique. Now you should be able to own that technique, right? Next time, whenever you see something with radicals, that's a very good technique for us to consider. Now that you have found the slope, we're going to find the slope at that particular point. So this is f prime of x. So all you have to do is find what x is in that point and plug it in. So in this point, 1, 1, the x value is 1. So I'm going to replace x with 1, x with 1. So I end up having 2 all over 2 times square root of 1. The square root of 1 is 1. So I'm left with 1 over 2. For this point, the x value is 4. So I replace that in here. And now we have f prime of 4 is equal to 1 over 2 times the square root of 4. The square root of 4 is 2. So 2 times 2 is 4. So 1 over 4. And then lastly, we're going to answer the last part of the question. Discuss the behavior of the function at 0, 0. So I'm going to see what happens to the slope at 0, 0. So I'm going to look at the derivative. So here you have x. The x value of this point is 0. So plug in 0 for the derivative, and that gives you 1 over 2 times the square root of 0. The square root of 0 is 0 times 2 is 0. So you have 1 over 0. It's going to be undefined. So what I'm saying that the slope of the function at 0, 0 is undefined. Hence, the graph of f has a vertical tangent line. So it has a vertical tangent line in that point. And then next example, we'll do the same thing. We'll talk about the derivative again. And we'll find the derivative with respect to t of the function. So in this example, the main thing is that we're dealing with the fraction, but also when you guys to get used to that, it's not always about x. You can define a function in terms of different variables. In this case, we're defining in terms of t. All right, so let's find and which is actually very common for us to use it as well. So let's find the derivative. So in this case, we're going to assume, well, we're going to set y to be the function of t, So we're going to take the derivative of it, and remember that this is the notation of a derivative of y in respect to t. So the limit as h goes to 0 of the difference of quotient, we're going to do the same thing. F of t is pretty much, let me write it here, 2 over t. So all we have to do is copy and paste that in here, and that's what we did, followed by the minus, and then now let's do f of t plus h. So replace t with t plus h. So replace the t with t plus h. I put the parentheses to be clear to the reader that this whole thing is underneath the 2, and you should put those parentheses as well. On the next line, we continue with the limit, and the technique that you want to approach here is you want to have one single big fraction bar on top. So obviously what we need to do is have common denominator. So the common denominator will be the product of those two. So multiply the t on this side, top and bottom, and multiply the t plus h, top and bottom on this side. So now they both have, on the bottom part, the same denominator. But on the top now we have 2t, and on the top over here we have minus 2 times the quantity of the sum t plus h, all over the same denominator, right? All over h, over 1. So we'll distribute the 2 here, and that's what I did in the next line. So we have 2t minus 2h all over t times the t plus h. Don't forget the limit. And then what I did here is, because I have a fraction over a fraction, I decided to change this to a product by multiplying the numerator by the reciprocal of the denominator. So instead of having multiplied by h over 1, I'm multiplying by 1 over h. Alright, so by doing this, now we have those two cancel each other out. We're left with negative 2h. And notice what happens with the h's. Again, you're supposed to be left with a term that, all terms that contain just an h. So we do. So we cancel that h and that h. You're left with negative 2 over t times the quantity t plus h. And we still have the limit, right? We haven't applied the limit. But now, because this one is gone, now we can try it. So replace h with 0. And now we have 2 t times t, and that gives us negative 2 over t squared. That's the derivative. We have found the derivative. So dy over dt is equal to negative 2 over t squared. All right, so we do have other ways to describe this derivative. This one is not, I don't use this one as much. Because I try to give you guys work on one single one, but sometimes it's beneficial to work with the other formulas of the derivative. So there's another one that says that you can take the derivative of a function at a specific value of c by taking the difference between your y's over the difference of x's as x gets closer to c. So it's the same formula. It's the same formula as before. What happens here is that you have the 2 points there, and they're getting closer by making this smaller, right? By making x get closer and closer to c, then the points of those two get closer and closer, so you're able to find the tangent line. But the benefit of that is that we can use that from the left side and the right side, and that will give us a different approach to finding the derivative. So this is known as the one-sided limit. Which are called derivatives from the left and from the right, respectively. It follows that f is differentiable on the closed interval a to b. It is differentiable on the open interval a b. So if it's differentiable on the closed interval, then it's also if it is differentiable on the open interval a b. And if the derivative from right of a and the derivative from the left of b both exist. So to show that, so what this line is saying is, if you want to show that a function is differentiable on the closed interval, you have to show that it's differentiable on an open interval and that it is differentiable on the right side of a and on the left side of b. Okay, so we're going to show that this is not differentiable at x equals 0. This is not differentiable at x equals 0. And the reason why this is not differentiable at x equals 0 is because the limit does not exist. The limit, in order for you to be differentiable at x equals 0, the limit of the derivative must be the same, right? It must exist, so these two need to be the same in order for this to exist. So these need to be the same. So what we're going to do here is we're going to show that this is not differentiable, and this is a very good way to show that something is not differentiable because you're approaching from both sides. So this is a good technique to remember when you're trying to show that something is not differentiable. So let's try this. Given the function, when the function is not continuous at x equals c, it is also not differentiable at x equals c. For instance, the greatest integer function f of x equals the greatest integer of x is not continuous at x equals 0, and so it is not differentiable at x equals 0. So we can see here that f of x minus f of 0 over x minus 0 coming from the left side of 0 will be, well, what do we know? What do we know about f of x? This is the greatest integer. What do we know of f of 0? It's going to be 0. And x minus 0 is x. Well, what do we know about that? Well, this is the greatest integer over x. And as we come in from the left side, this is going to approach in, this is going to approach it's going to approach infinity, yes. And then on the right side, we're going to approach 0, right? So on the right side is going to approach 0, as we can see in the picture here. All right, so then therefore those two are not going to each other, so therefore the function is not differentiable at x equals c. Let's look at another example here. We're going to show the function the absolute value x minus 2 is continuous at x equals 2. The one-sided limit, however, shows that the limit of f of x minus f of 2 over x minus 2 coming from the left side, we'll see how that will help us. So f of x is the function, which is right there, f of 2. If we plug in 2 here, you have 2 minus 2, the absolute of 2 is 0. And then on the bottom part, you have x minus 2, right? X minus 2. Now, what do we have here is the limit of that coming from the left. We know that this is, it's a negative value, right? We have a negative value because this number is coming from the left side. So this number is smaller than 2. A small number minus 2 will be negative, but the absolute value is going to make it positive. A smaller number than 2 will make this be negative because you're subtracting a small number minus a bigger number. This will be negative, so you have positive over negative will become negative 1. In a similar way, we can have that of the limit of f of x minus f of 2 all over x minus 2 coming from the right side. Well, this number is bigger than 2, so a bigger number minus 2 would be a positive, and the absolute value of positive is positive. Here, the same thing. Here, this is a number of 2, a number greater than 2, so a number greater than 2 minus 2 will be positive. So you have positive or positive will give you 1, and that's a 1. So those two are different, so therefore the limit does not exist. So if you notice here, the function is not differentiable at x equals 2, but it is continuous, right? It is not differentiable because at that point there's two different slopes, right? One is coming this way and the other one's coming that way. So it's not differential with a point and the graph, which is at the sharp turn or on the vertical tangent line. So when you guys looking at the graph, if you're looking at the graph, the best way to know whether the graph is differential or not is that the graph needs to be smooth. If it's smooth, then it's differentiable. But as soon as you get a corner, that corner is not differentiable at that point, at that moment, at that instant. But other than that, it is differentiable everywhere else. So corners or vertical tangent lines means that it's not differentiable, that the function is not differentiable there. And so the last part, we can kind of conclude this, right? If you're not continuous, then you're not differentiable. Now you could be continuous and not be differentiable. So the next line tells us that something very important. If f is differentiable at C, then this will guarantee that f is continuous at C. Let me say that again. If f is differentiable at C, then this will guarantee that f is continuous at C. Now we gotta be careful because the opposite of this is not true. Meaning, if f is continuous at C, doesn't mean that it is differentiable at C, as we can see in this perfect example. This is continuous at 2, but is not differentiable at 2. So be careful how you use this theorem. And I sort of kind of imply that in these two notes. In relation between the continuity and differentiability is summarized below. If function is differentiable at C, then it is continuous at C. So differentiability implies continuity. It is possible for a function to be continuous at C and not be differentiable at C. So continuity does not imply differentiability. All right, I hope you guys find this helpful. We'll try a few more examples in class, but please go over these notes, review them. If you need to watch the video again, make sure you guys do that. All right, have a great day. Thank you. Bye.